For the second experiment, what we did was, first of all, we fill a glass container 3/4 of its capacity. Then, with a marker, we draw a line in the container to indicate the original height of the water. After that, we shape a sphere of modeling clay and we put it into the container. Using a different marker, we draw another line marking the rise of the water on the container. Then with a syringe, we remove the water until it reaches the original height and we put that water in a beaker. Then we do almost the exact same thing, but instead of having a sphere of clay, we turn that clay into a ship. We also have to mark the level of water that it's at first before we put the ship. Once we put the ship into the water and it's floating, we mark the new level of water that it rises. And again, we took the water out with a syringe and we put it in a different beaker. After that, we use a scale and measure the mass of the water of each beaker and of the modeling clay. Once we got those measures, we use them to get the buoyant force exerted on the sphere and on the ship. Then we compare them with the weight of the modeling clay. To get the buoyant force, we use the formula density times volume times gravity, using the density of the water, which is 1000, the volume of the sphere, which is 0.4091,125 meters cubic, and the gravity, which is 9.81 meters over second square. And by multiplying all of these numbers, we get 0.8939 newtons. The second equation was weight equals mass times gravity or acceleration. And in this case, we use the mass of the clay, which is 0.08 kilograms, times the gravity, which is 9.81 meters over second square. And when we multiply those numbers, we get 0.7848 kilograms.
Third experiment. First, we measure the area of the pistons of the syringes. Then, we fill the hose with red oil and join each side of the hose to each of the two syringes, the one of 20 mm empty and the one of 3 mm filled. We place an object of 500 grams on the 20 mm syringe and apply pressure to the small syringe. In this experiment, the first thing that we have to get is the area of each piston. In the case of the 20 mm piston, we had a diameter of 2 centimeters and the total area was 3.1416 centimeters squared. In the case of the 3 mm piston, we had a diameter of 1 centimeter and the total area was 0.7854 centimeters squared. Then we have to get the force applied in the 20 mm syringe according to the mass of 500 grams that was placed on top of it. And we use the formula force equals to mass times acceleration. The mass was 500 grams and the acceleration is 9.81. The total force is 4,905 newtons. Then to know the force on the 3 mm syringe, we had to use the Pascal's principle. Force 1 over area 1 equals to force 2 over area 2. Force 2 was 4,905 newtons and the area 2 was 0.7854 centimeters squared. All of this times 3.1416 centimeters squared, that was area 1, to get force 1, that was 6,245.223 newtons.
For the third experiment, we had a bottle which measures were 11 centimeters of length and 15 centimeters of height. We had two hoses, and the time that the water make from the first hose to the bottle was 15 seconds, and for the second hose, the water took 13 seconds to arrive to the bottle. After that, we had to calculate the difference of pressures between one water in one of the hoses and the water and the other hose. In order to do that, we had to calculate the speed that the water makes in both hoses and how much time it gets to fulfill the bottle. So the time of the first hose was 15 seconds. So the formula V over T equals to V times A would give us the result of the first velocity. But for that, we have to calculate the area and then the volume. So area is equal to P times radius to the square, which makes 0.95033 meters squared. Then the formula for volume is V equals to A times H. So we multiply 0.95 times 0.15, which gives us 0.1425 meters squared. After that, we just divide the volume over the time, that was 15 seconds, and that would be equal to the velocity of the water times the area. So the volume over time would be 0.1425 over 15, which is equal to velocity times 0.95. So 0.14 over 15 it's equal to 9.5 times 10 elevated to the minus 3. After that, we just have to pass the area, that is multiplying the V, dividing. So it would be 9.5 times 10 elevated to the minus 3 over 1.95. That would give us the velocity, and the velocity it's equal to 9.996527522 times 10 elevated to the minus 3. So that would be our first velocity. To the second velocity, we do exactly the same, except we substitute the time not by 15 but by 13. At the end, the result gives us a value of 0.01153846 meters per second. After that, to get the differences between the pressures, we have to use the Bernoulli's equation, which is equal to P1 plus a half of the density times V to the square plus the density times the gravity times the height equals to P2 plus 1/2 of the density times the volume squared plus the density times gravity times the second height. After that, we just substitute the values that we already have. The density is equal to 1,000 kilograms per meter square. That we have to multiply it by 9.99 times 10 elevated to the minus 3, and that we have to add another density, which means another 1,000 kilograms per meter squared, and all of that would be equal to P1 times, plus 0.99 plus 1,470. So at the end, if we do all the math, we have that P1 plus 1,470.049 equals to P2 plus 1,470.06. Now that would be the same as saying that P1 plus 1470.049 minus 1470.06 equals to P2. So it would mean that P1 minus 0.016, because the 1470.64, you have to rest the 1470.06. So at the end it would be 0.016. So P1 minus 0.016 equals to P2. So now you can say that the difference between pressures is P1 minus P2 equals to 0.01659.